Okay, in the next 40-45 minutes, I'll try to fulfill two major tasks. First, I'll try to tell the story behind, essentially try to analyze, maybe a little bit superficially and personally, a sequence of the events which led to this lecture here. And the second one, I'll try, in the second part of the lecture, I'll try to persuade you that graphene is really a magic material with plenty of interesting properties to discuss. Okay, let me start my story with one transparency here. So it's appropriate time. It's my PhD, 33 years ago. The only thing, in addition to hammer and sickle, I like to write the title of this PhD. It was Investigation of Mechanisms of Transport Relaxation in Metals by a Helicon Resonance Method. Does it sound exciting for you? So let me assure you that at that time is as exciting as it sounds now. So, but every cloud has its silver lining, so the message I took with me for the rest of my life is, and hope some of the professors will be influenced with this message, never torture your students by boring projects. And I followed this line for many, many years. After PhD, I have become a staff scientist in Chernogolovka for 3 years, and the first time was to build some new area of research, to try something new, but different from everything else, but available at the same time with Soviet facilities, which at that time was nearly an oxymoron, new and possible. Facilities were not that good, but looking around, my first study in system was something, a superconductor projects strongly inhomogeneous magnetic field on a studied system, and for quite some time I enjoyed it. It was reasonably well-cited papers, a set of papers, how electrons behave in such strongly inhomogeneous field. I don't want to speak about this, but a message and experience I took away, it's very nice to find a new phenomenon in a well-studied system, but it's much more rewarding to find a new experimental system where you can hope to find many phenomena. So it influenced me, so for the rest of my career, I was looking for new experimental systems, if you wish. When the Soviet Union was completely damaged at the age of 32, and with Hirsch index 1, which was mostly due to self-citations, I entered the job market in the West. Okay, so it was quite a rapid learning curve with many different phenomena I studied at that time. I learned a lot about semiconducting physics and so on, got experience because 4 places more essentially, each time a different subject to study. One example I like to bring from those years is the following. During my first 6 months visit at the University of Nottingham, it's very hard to find something for an experimentalist to do within 6 months. So I tried my best, and my hosts at the moment, okay, could only find some samples which were studied 2 or 3 years ago, everything done and dusted, forgotten. They gave me those samples. And, no one expected anything, but within half a year, we managed to get enough new results for a couple of decent quality of publications. So you can take this as an experience, and this is what I usually say when people come to me complaining about samples. No such things as bad samples, only bad postdocs of PhD students with this. And my younger colleagues really hate this saying. Yeah. Then I moved on and got my first tenured position in Nijmegen, and again, it was important. The same task I got after PhD to find in research niche. Facilities were, of course, better than in Russia, but I had still to combine what other labs make available, some lithography done from Russia, structures from Nottingham, measurements there, and okay, after 3 desperate years, we start publishing something which I call mesoscopic superconductivity, how vortices is arranged in circuits. And as you see from here, there was a string of high-quality publications coming out. So, yeah, that was a backbone. And on the top of this backbone, there was a possibility to innovate, to think about moving and so on. And it was my first experience of what we call these days Friday night experiments, although it doesn't require to be done on Friday. We had, in this lab, we had big magnets. They were ancient, sort of 30 years old. They consumed gigawatts of power and were not very good, well suited for doing experiments I was interested in, and so, but I had a pressure to do something with those facilities because they provided some funding. So the competitive advantage, I found out that many people have similar strength magnetic fields, but we had a room temperature bore, which not many people did have at the time. So I also knew that there is such things as magnetic water. Allegedly, you can go to a shop where you can buy magnetic water descaler. You allegedly put it on a water tap, and instead of this shock and calcination, suddenly your kettles might or might not become free from this scaling phenomena. I have nothing to contribute to the physics behind, if there is any physics at all. It's very controversial phenomena, but I thought, okay, if so small magnet can do something to water, what if we put water in very high magnetic field? So my first approach was just to pour water inside the magnet, and I didn't really expect anything to happen, but surprisingly, what happened, the water stuck somewhere here, and this is what you see from the top. Water levitates inside the magnets, and it's very nice, very calming movie. I love to watch for minutes and maybe hours. So nice. It took essentially only half an hour to make all the calculations and find out that the phenomena behind this diamagnet is very simple phenomena, that substances which assume to be non-magnetic are in fact this diamagnet is not that small. So I was happy for a while, but then found that 5 years ago I was already scooped. Okay, people reported levitation on non-magnetic matter in strong magnetic field before, and yeah, it was a disappointment. But when I saw this paper, I thought something is missing. It's not really a scientific paper because there is no plot, there is no picture. And this is why neither myself nor colleagues ever noticed this. Actually, no one. People for a couple of weeks, for a few months, believed that it was a joke, rather than when I'm saying we can levitate everything inside the magnet, no one believed. And I thought we need an emphasis to make people aware that even non-magnetic substances can be influenced strongly by magnetic field, and Yeah, okay. People, my colleagues came with brilliant ideas. What can we levitate else in the magnet? And yeah, whatever you put there levitates equally. It doesn't matter whether it's flesh or bones or cheese or piece of wood or a stone. Nearly the same is equally diamagnetic. So the best candidate was the frog, a poor frog. It was very difficult experiment, unlike people like myself don't use to frogs who jump and etc. and put it in a very precise position in the magnet. It took me a lot of trouble. Of course, frog caused a lot of hype around with more publicity than the Nobel Prize normally causes, and but behind all this superficial hype, there was something more important, at least among my colleagues. I very often go to conference and people say, "Oh, I know you. I don't understand anything about graphene," but I show the picture of this frog to my students who immediately like to learn why it levitates, how it's possible. And in a sense, it was a perception change. I think in the community, diamagnetism is not perceived as an extremely small, negligible phenomena anymore. So what experience I learned from that? It's even look for a competitive edge, and even Asian facilities sometimes may offer you some. And the second is, due to my Ig Nobel Prize, I learned not to take myself too seriously and my research as well, which is always nice feeling, especially after receiving the Nobel Prize. It will keep me sane, I hope. Time was to move on, and I got a chair in Manchester. Came because my wife also was offered a position there. Empty lab, little startup, no central microfabrication. So first to establish yourself and facilities, we start moving and start working and start publishing. And the British system works this way. If you prove that you can deliver not only words but decent quality results, that they sponsor you quite well, and within 3 years we get well-equipped lab and own state-of-the-art microfabrication. That's quite unusual for any country, and Britain is good for active people. So at that time, after establishing myself, you know, like learning to ride a bicycle, you never forget it. So an idea to move in somewhere sideways from your main research direction was going through, and I learned in literature how this magnificent animal climbs walls and ceilings. The mechanism is quite simple in van der Waals force. Toes of geckos are covered with millions, billions of tiny hairs. Each hair attaches with minute force to an opposite surface, and it's minute, but when billions of forces are accumulated, put together, it's formidable force enough to keep geckos on ceilings. So what shocked me in this mechanism, which was described in publications, that it's so simple, and the scale at the same time, it's submicron, exactly what we're doing in the lab. And the idea, and this Friday night experiment, was to try to create artificial hairs on the same scale. And it's never worked as good as with geckos, but it was good enough to demonstrate the concept, to prove the concept, and it's a big research area at the moment, and people trying to commercialize and so on research. Again, learning how to make an emphasis. We produced only 1 by 1 centimeter patch of this gecko tape, not enough to let students climb out of the windows, but enough to put a toy on a glass ceiling. So people like the idea of Friday night experiments, and I always try to say that, you know, we had so many failures, and I try to list those. There were at least 20 or 30 of those failures over the time. But when I list it, it's a new experience for me. I realized that out of those 20 or 30, we had, 3, 4 successes, and which is a huge proportion, which probably I try to understand why it's so. It probably tells you when you move from one area into another area, doesn't matter whether your idea is great or not so great, it gives you a much better chance of finding something new than within an area covered by yourself and colleagues for many years. So I'm still mulling it over. So this is time to come to the history of graphene, which initially was along the same lines. Try to poke into sideways and see what happens. So the idea came, the basic idea came from 3 thought clouds. One was metallic electronics. Essentially, if you have a piece of metal and apply electric field, you can change, attract or repel electrons in this layer and change the conductivity. So that's so simple that after J.J. Thomson, a famous British scientist, discovered the electron, he gave to his PhD student Charles Mott, who is the father of Sir Neville Mott, who won the Nobel Prize 30 years or 40 years ago. He gave the project to do this metallic transistor, if you wish. It's never succeeded, and people were trying and trying. And the reason is that you induce only very small changes in concentration. If you compare those changes with the number of electrons per layer in a typical metal, you'll find out that it's a small percentage change. People use mostly bismuth, and should be bigger change, but no one has found anything more than a few % change. Disappointed. Idea is good, but the result is disappointed. So can we deal with anything like that? Of course, I was influenced by carbon nanotube boom, which is in 90s. Many people published so many beautiful papers, and I was salivating looking at how beautiful those results are. And it somehow pushed me in the direction of thinking about metallic electronics with carbon. And the final thought cloud, which was intentional, was to read literature about graphite. It's a huge literature about graphite, but graphite is still badly investigated compound, and it was essentially nothing known about thin films of graphite, which are impossible to evaporate or something, or produce in normal techniques usually produced for metals like gold, silver, bismuth. So all those clouds somehow merged together into a project which I gave not so long ago, 8 years ago, to a new Chinese PhD student, Da Jian, to make graphite films as thin as possible and to study whatever the next day will send to us. Okay, metallic electronics, if you wish. Not so important that it's a new experimental system again. So I bought for $300 a piece of graphite and asked him to polish it as thin as possible. So 2 months later, he comes to my lab and saying, I have done it. And this is a Petri dish and tiny flake at the bottom of this Petri dish. And I look in the microscope, say, see 5-10 microns in thickness. No, we're not going to do that. Could you try to make even thinner, use another powder to polish? And he tells me, can I get another piece of this one? So essentially he polished away all the piece from the beginning to the end to do those. But it was my fault. I gave him a wrong actually material in a matter not what I intended to do. Highly oriented density pyrolytic graphite instead of highly oriented one. So this is where the legend of Scotch tape came through. Oleg Shklarevsky, a senior postdoc, was present during our exchange of opinions how tablets should be polished, whether a piece should be polished or a whole to get a small flake. He said, "Why you're doing this?" Okay. And he ran away and brought a piece of tape, which are just attached and then detached to the surface of graphite. And comparing what is there with what is here, was obvious that polishing was not a good idea at all. So yeah, Scotch tape was the idea we started using later. So if you look through it was much thinner than this one. And if you look on transmission, you find out that within this region there are very thin pieces which are transparent. This one, with the benefit of hindsight, we know that it's probably only about 10 layers. We didn't know this before, but it was a way to get it. So, and we use and still use approximately the same technique. Initially, it took a few months to go down to small pieces of single layers, and a couple of years later, we managed to get a single layer which is visible by naked eye. What you see here, it's a single crystal of graphene and deposited on oxidized silicon surface. Amazingly that you can see it with your naked eye. Amazingly that it's a single layer, and it's not big, but to make experiments, to make proof of concept devices, we don't need any more. You can make thousands of devices from one such big, not industrial application, of course. So if it would be just observation like it was there, some people say, oh, they isolated graphene, that's great, and this is it. If we left at that moment showing that there are monolayers of graphene lead, it would be, well, whatever, maybe a publication, and no one would care about this. What was important, we went further. Already at the very first stage, we start picking up flakes of graphite by tweezers and depositing them on glass slides and oxidized, maybe moving in the direction of transistors or metallic electronics. What you see here, one of our first devices, that's a piece of graphene covered with oily substance, comes from silver paint, which makes 4 contacts. The size here is a cross-section of your hair. So this device was made under the microscope with toothpicks and so on. It looks ugly, but this is a very skillful experiment to do something like that using only your hands. Not many people, Konstantin Novoselov, my co-recipient, myself, maybe 1 or 2 other postdocs can do similar experiments. Still easier than levitating the frog, but a masterpiece in this sense. Yeah, so we start looking how the device conducts, and it's conducted well. And what is most importantly, it started to respond to this electric field. Its changes were already of the order of few percent, much more than people found previously in metallic electronics. Of course, only a madman can say that it's a transistor if changes are of the order of 1%. But for me, it was eureka moment, because I thought such an ugly looking device made by hands essentially, with no facilities applied, already shows some response. What would we do if we make thinner, use all the range of facilities which were already available at the lab? So we try to push further and further, use electron lithography, went down to a single layer, and after a lot of hard work and plenty of experiments, a year later we published this paper cited by the Royal Swedish Academy. So a remarkable thing about this paper was how hard it was to publish it. It's most cited paper on graphene, but it's not only, it's probably information of 3 or 4 papers included, but in addition it was twice rejected by Nature, 2 previous submissions. So if you wish a message to take away, if you recently have been rejected from one of those glossy journals, don't give up. It might be a Nobel Prize winning paper. So why this paper was important, okay, or turned out this important? Of course, okay, we observed this isolated graphene in big enough sizes to do experiments, and the method was simple and accessible to other groups. But as I said, it would be forgotten immediately. More importantly, we have shown that we can control electronic properties by external means. What essentially means, if you evaporate a film of gold, it will stay a film of gold. Whatever you do, you can't really change the material. Here, by applying voltage to the substrate, we change it from a good metal with electrons like charge carriers to a good metal with positive charges as carriers through a state which very essentially a semiconducting state where resistance grows with decrease in temperature and so on. It's a huge change in properties and change in resistance, not by 1%, but by a factor of 100. Even more importantly, what no one could possibly predict, that the quality of the material would be high. The graphene is placed on a rough substrate, covered with adsorbates, all sorts of rubbish around, and still electrons move through the material like bullets without feeling what is outside. The weather outside, ambient conditions are not important. It's completely counterintuitive. The thinner the film you usually make, the worse its properties. And now we are dealing essentially with surface science, but without high vacuum and 2 surfaces exposed, you expect rubbish. If it would be, quality would be, say, 100,000 times less, it would be never an interesting experimental system, but the quality that it's so high was really important. So, in a sense, this observation, 2 observations, allowed to show that the material is really an interesting system, and people start moving into this area, hoping to find many more. And over the years, we have found many phenomena and many applications. And the last part of my talk is to describe those properties and applications. So, on the first side, it's carbon all over the place. It's a very simple material, and you don't expect any complexity from this material. It turned out that despite being so simple, the material has a huge range of superlatives to characterize it. Of course, it's the thinnest material you can imagine. Because of that, it has the largest surface area. 1 gram can cover several football pitches. In Manchester, we measure surface in football pitches, as you know. And it's stronger than diamond, of course, on nanoscale, taking into account the thickness. But it's so strong, it survives ambient conditions. If you make a thin membrane and poke with your hair and so on, it survives really easy. A membrane can sustain a pressure of a couple of atmospheres depending on size. It's really amazingly that it survives. It's stiffer than diamond. Stiffest we know. Nevertheless, it's pliable and stretchable material, unlike diamond and so on. It's a little bit like rubber, combines properties of rubber and diamond, if you wish. It outperforms conductivity of diamond, previous record holder. It outperforms current density at room temperatures. It can carry silver or copper. It's completely impermeable to gases and liquids, and it shows a range of amazing electron properties, and the list goes on. I don't think that any material in the history attracted so many superlatives. So one of those concerning electron properties, let me tell what was the driving force for the last 4 or 5 years in this material. In one cartoon, I try to explain this. It's a difficult task. Essentially, all materials we know, their charge carriers and most of their properties can be described by electrons moving like bullets, and interaction with the crystal lattice is described by star, effective mass. It's not the mass of electrons, it's mass of some imaginary particle moving through the material. And this is it. Material scientists, all material and condensed matter physics use this simple equation with some additional terms, and we enjoy playing with this, and most properties can describe this. Particle physicists, astrophysicists, they deal with another equation, essentially with this equation. In the limit when your speed is so high that you can neglect the rest mass of your particles, you go to so-called Dirac equation, and this is very important equation in relativistic particle physics. But that's our world of quantum physics, two equations. So where graphene comes into play, that interaction of electron waves with this honeycomb lattice of graphene creates charge carriers which mimic the same equation. It's nothing relativistic is about charge carriers is graphene, but the mimicry is absolute. Except instead of speed of light, you have Fermi velocity, which is very high, but 300 times less than speed of light, and instead of real spin, which rotates everywhere here, you get an index of the sublattice. But if you like to study this equation, graphene offers you a possibility. If you put two layers on top of each other, you get yet another equation where you have a combination of those two. I have no time to discuss this one, but if you wish, the possibilities to study quantum physics just increase by a factor of 2 due to the presence of graphene, and you can learn a lot about quantum physics. I'll give you only 2 examples of what sort of physics comes into play. You know that you can't walk through the wall, but electrons can go through potential barriers if they're thin or not high enough. It's called tunneling. Oskar Klein, a Swedish physicist, 80 years ago, he solved not Schrödinger equation, but this Dirac equation, ultra-relativistic equation, for the same problem, and found out what is known as Klein paradox, that ultra-relativistic particles can't be confined. They go through the barrier however thick or however high this barrier is, and it was known as Klein paradox. No one even attempted to look experimentally into this problem because it couldn't be, this experiment couldn't be set up. What we did, we rearranged this problem theoretically 4 years ago, showing that in graphene you can test this phenomena, and this routinely happens in graphene. It was demonstrated that indeed charge carriers can be confined because they follow this Klein paradox tunneling phenomena. Very, very cute that you can address such ancient problems experimentally after some times. My other example is extremely simple. You can probably do it even at home. You get an aperture and cover this aperture with graphene. So to look through the aperture, just how light goes through the aperture. And in this case, it's intentionally broken aperture. Here, light goes completely through. That's one layer graphene. It's bilayer graphene. What you see here is essentially a single crystal, which one layer of atoms, and it still absorbs a lot of light, 2.3% to be accurate, and it's boring flat spectrum without any features. And you think, okay, what can I learn about this? But then with the help of physics, you'll find out that Joule losses as light goes through tell you that the conductivity at high frequencies of this material is universal, and the opacity of the material is given pi times the fine structure constant. So when you observe this opacity of graphene, you probe with your naked eye, either pi or phi structure constant, whatever you want. What you do in this experiment, you probe coupling of light with relativistic like charges, and this coupling is described by the coupling constant, which is also known as the fine structure constant, of course. But in a very simple observational experiment, you can probe such fundamental constants as well. So 2 examples, probably not enough, but let me assure you that there are many more similar examples, and this is probably what graphene has brought us during the last 5 years, a real cornucopia of new science and so on. Because this is audience not of physics experts and so on, so I think it will be not a full story if I'll just finish with this without discussing applications. Applications, 2 years ago, it was impossible to even speculate about those because there was no way of industrial production, and I usually try to find an excuse not discussing applications by telling the story. I think I have a couple of minutes to tell this story. Do I have a couple of minutes to tell the story? So essentially, once I was on a boat trip watching dolphins. Dolphins, magnificent animals, and on this particular trip, somehow they were trying to play with humans. Very unusual, actually, for wild animals. And they were swimming along the boat, not begging for food, begging actually for touch. And everyone was leaning over the boat trying to touch these wild animals, and romantic moments, completely everyone silence, everyone at awe. And then, a little boy behind suddenly shouts, "Can we eat them?" So, spoiled, everything spoiled. So in a sense, until recently, graphene was like this romantic moment of studying physics and fundamental phenomena and funding agencies and so on, saying, can you do something useful about this one? And Prussia. But you can think immediately about what can you do. Each superlative offers something compatible, competitive with other structures. And let me just give you a few examples, what is possible. List is big, and I have to put a disclaimer. I don't think that Nobel Prize was given to me for applications. It was just for bringing the attention of this one, and it goes beyond the Nobel lecture, what will be the future hold for us. So what could be in future? Okay. Already in our first paper, finding such nice properties, metallic electronics, if you wish, we speculated that we can make so-called ballistic transistors which would work at very high frequencies. It was blah, 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 if you wish, and no progress for quite a few years, but then US military put a lot of money for this very narrow-minded project for telecommunications to put to make on sale transistors, half terahertz frequency transistors. And within a year or two, people start demonstrating something like 100 gigahertz very quickly. And this year, they went nearly to the limit, and industrial scale of production was demonstrated as well. And this is as good as any other material could be. This would better than anything else. So it's very competitive. Still remains to be seen whether we can go to terahertz, but it looks very promising transistor and emitter of ultra high frequencies in this case, and very short period of time. Another example, it came within a year or two, is for chemists present here, especially for the president of Chalmers University. And you can consider graphene as a material science, but you can consider this material as a giant molecule, just the same molecule as benzene, but without any limitations in size. And you can ask yourself whether this molecule can take part in the same type of chemical reaction, rather than being peppered with adsorbates, whether it can be another stoichiometric compound, completely different material. So we have demonstrated a couple of those. This is probably where you can see it. It's a collection of graphene flakes. Otherwise, we can't handle it with tweezers and couldn't see it because it would be transparent. It's a layer after layer of graphene, and you expose it to atomic fluorine, and after a few hours you get a completely different material which is stoichiometric and transparent, insulating, and what unusual, it's thermally stable and chemically inert, similar to Teflon. But unlike Teflon, it still inherits this property of graphene, its strength. We call this material fluorographene or two-dimensional Teflon, and I personally very excited to see probably in future what would happen if we put flakes of graphene inside Teflon, which is known to be scratchable material, and maybe we get much stronger material than current Teflon, and maybe housewives will put a memorial to this material for non-scratching cookware. Example which came, one of the last which came very recently. I had no idea about this until last year, and it's put here to show that the area still develops very quickly and in very unexpected directions. Because I presume that there are life sciences in this audience, it would be probably good to discuss. So the idea is to put a thin membrane of graphene and pull DNA through and see what's happening. So far people did this, and they see events where DNA blocks this hole, and when this hole is free. Actually, it's very far from what we want. We want to get two electrodes here and here, and this part would be non-conductive, and when pulling DNA this gap is filled either with T, G, or A base of DNA, and on your computer screen you get a signal T, H, A's, and as you pull DNA through the whole sequence coming out of your DNA, if you can make this for $10 or $100 for every one of us would get this sort of DNA profiling, and probably would help in medicine alone. Why graphene? People did try this with other materials, but whatever you do, it's so thick that everything, many bases go along this thickness and everything average out. This material was shown to have effective thickness of only, less than the base. So this is the only one which offers this possibility to see it at the level of individual bases. We'll see what develops, but I can't exclude that within 5-10 years it will work out and it will be exciting development for graphene. Coming back to the reality, I'll give you final example what seems to be determined to have happened. All mobile phones, all computer screens and everything has some transparent conductive material which usually called indium tin oxide, and the function is very simple. It has to conduct electricity and allow light to pass through. Graphene has high transparency and reasonably well conductive, but it has also an advantage that it's chemically inert and flexible. So the idea in all those gadgets where currently ITO is used to use graphene instead, it was a speculation for quite some time, but then, it was a working cell, but very small, few microns, before 2008, before industrial production. But nowadays, people can produce that big roll-on production of graphene in very industrial qualities and at decent price for $50 per square meter, and very competitive parameters describing conductivity and transparency. So the idea, especially Samsung pushing through, is to use it in all sorts of gadgets. The easiest one is touch screens, and an additional advantage that because it's so flexible and pliable material, you can make those touch screens bendable and variable as additional functionality. They expect industrial production 2012, but I was promised to give a mobile phone with graphene touch screen if I'll come summer 2011 to Korea. Whether it was an advertisement trick or not, I don't know, but it's very close to production. So I think, let me finish with this transparency. It's usually a very long and painful way for any material from an academic lab to commercialization. In this particular lab, probably graphene again beat the record in Superlative as the quickest material who reached the industrial lab only within 5 years. So, in this transparency, I like to thank my collaborators, especially my co-recipient, Konstantin Novoselov, and my wife, who was on the same paper and which attracted the Nobel citation, and many other collaborators. And I also would like to say thank you for listening me here and having me here. Thank you.